Come back to the channel, and then we're solving this extra characters in the string problem. So you're given a zero index string S and a dictionary of words. So you have to break S into one or more non-overlapping substring. I mean, that just means that you can reuse the characters that part of one of the words. And yeah, so there may be some of the extra characters, then we want to return the minimum number of extra characters left. So in this case, like lead code, so the dictionary gives you lead code and lead code. So you can see, you can break down like this part as lead and then this part as code, and then you like leaving this as. So as is the extra characters, and you only have one remaining, so your output will be one. Right. So when coming up these questions, and actually you just look at the topics that tell you try. So, and then they also tell you dynamic programming, because you will know there will be a lot of recursion call, and using DP can save a lot of time counting the same recursion call. So in my solution today, I'll teach you how to build a trie, and then how to use a trie to solve the problem. So if you haven't used a trie before, it's actually like a tree. So let's get in here. So a trie is like a tree. So let's say lead code, right? Let's say I have lead code. Okay. Let's say I have the dictionary, lead and code. Let's say just two of this. So this is your root, means nothing, and then you just go into have a L E E T, and then you will just mark the end of a word. Let's say I mark this to be true, means when you just look at lead, like L, it's not a valid word. If you look at LE, it's not a valid word. But when you look at LET, lead, this is a valid word. So this is how it means. And then you can just build a code right here. So if I want to say, and then you're going to mark this, or if you have something start with a CO, okay, code, and code, let's say you have code, COLD, and then it will just extend it this way. So the all will just means like it's like a tree, right? This is the parents, and then you have your children right here. So then this is the end of word, and you mark this to be the end of word. This is how a trie word, and it looks like a tree. And then you can have as many children you want. So I think the root can has up to 26 because there are only 26 characters. But if you want to like have special characters as well, then you can also put that in. But I don't think this is something that we have to consider in this question, right? And since we use try, then we can just go in each of this character. Let's say I actually like to use this text box, say Apple Pen. Let's say I give you something called Apple Pen, and then I give you Apple and Pen. Another text box probably. Apple and Pen for the dictionary. So now we need to recursively check if we have this thing right here, right? So, well, let me make it bigger. So, oops, what? Okay. Let's say I have Apple and Pen, then I want to try to do this, right? This is a valid word, so I'll have like Apple, and then when we reach here, this is a valid word, and then pen, this is a valid word. So when we look at A, we see like, oh, A is not actually a valid word, then we can just skip this. Or we can, at the same time, we try to find if we're skipping this, what happened to here? What happened if we skip this and go here? What happened if we skip here and go here? So if we skip A, so there are two possibilities, right? We're using A or we skip A. So if we skip A, then we need to plus 1 to our result because we know this, like we're not using A. So A must be the extra characters. And then we just call recursively, maybe just call DFS because we're going into it. And then we call this, let's say this is current, then we say current plus 1. So this is one of the possibility. And then the other way is that we check if we include A in it. And then we go up to the end of this. All right, so I actually get this illustration from ChatGPT. So this is kind of something that looks like this. When you have like Apple Pen, then let's copy this over. Right. Let's say you have Apple Pen and right, you have Apple Pen and then you have the Apple and Pen thing. So first, there are two possibilities. One is you skip A. One is you match A, right? You use A in the end. So when you go ahead A and then P, P, L, E, eventually you hit this part and you're like, hey, we'll actually get this one, right? So at that point, you actually match Apple. So Apple is actually gone. So at this point, up from 0 up to 5 or 4, at this point, you do not have any extra characters. That's what happened right here, the matching. So this part, the matching one. And then to go ahead and call DSS 5, I think this is 0 indexing, so 5 is actually P, this pan P. And then just go ahead and see if you skip that P, and then you call, see, this part is skipping P, and then you go in, and then you see, hey, I didn't see anything P ending with or starting and ending with. So I go ahead and see E, and then skip E, and also skip N. So this part, when you hit the end of the queue, you just return 0. But this part will actually give you 3. Like when they call back up, this is plus 1, plus 1, plus 1. So just give it 3. And then this part will match it, right? So this will return you 0 because it doesn't have plus anything right here. So this part is 0. So when you return it, you just take the mean of this two and then see which one is lower. It's the same right here, right? Just go ahead and skip A, and then if you skip A, you probably you never match this PPLE again, right? Because there's no such word PPLE. So this just happened that when you skip A, you plus 1 to it, you skip P, you skip L, you skip E, and then that's like the fifth one, and then maybe you like add you find pen. This is actually like the same right here, right? Maybe you match pen, or you didn't match pen. If you didn't match pen, then you get 3 back. If you match pen, you get 0 back. And then they'll just take the mean of this, which is 0. And then this is plus 5 right here. So you get 5 plus 0, which is 5. So you return 5 and return 0 here. Then you take the mean of that. Then you get 0 for this Apple Pen. All right, that's a lot of talking. I think let's just dive into the code, and then let's try to build a trie tree and solve this problem. All right, let's look at the code. Right. So in the beginning, we need another class called TrieNode, and then we need to initialize it. Okay. Then this TrieNode need to have 2 things, which is the first one is the children, and then we also need its word. So its word is actually the trie thing that we show you. So initially by default everything will be false. This will be false. This will be false. It only turns true when we hit the end of the word. So this will be true. Where's my mouse? Okay, right here. This will be true. This will be true. Otherwise, this will be false, false, false. If it's not in the dictionary. All right. So by default, we set this to false. All right. So by that saying, we also need a build tree or build trie helper method, and then we just pass in self and dictionary. So let's just try with build trie. So we need to just initialize the root to be a trie node. This actually will just be something like placeholder to be a trie. And then we want to go through and pass every word in dictionary. So for word in dictionary. So what happened for every word in dictionary? We want to reset our current node to be the root because we're going to start building it from the top, right? So we say current equals to root. And now we want to go through every single character in the word. So for every single character in the word, we try to start building the trie. So the first thing we need to check is if the character already on the tree. So let's say now I'm trying to put code into lead code, right? I'm trying to add a code right here. So when I first go in, I want to check if C already here. So if C is already here, I don't want to create another C to here. This is not how like a trie is supposed to work. So first I need to check if it's already in here. If it's already in here, then it's fine. If it's not in here, then I need to append it. Like let's say now I want to do a dog or something, right? So D is not already in here. So I want to add D to be a new children. So if C not in current.children, then I want to make current equals to current.children, and then I add a C into it. Then when you finish all this thing, when you finish the whole word, so by the end of the word, it's actually the last character, and then your current is actually pointing at it right now. So if it's already pointing at it, so we want to make the isWord field to be equals to true. And then at the end, we just want to return the root. Okay, so this is part of the build trie. So now we need to go into doing the recursion thing over here. So first we just set length equals n equals the length of s because we're going to use it later, and then we can call it root equals to self.build trie. So now this will return you a whole trie as a root. So I think you call dictionary. Yep. Then we need a DFS function because we need to recursively call it, right? So we can say def DFS, and then I can set start where you want to start, right? And then if start equals n means that you hit the n of the length, then you just want to return 0 as what I showed in the visualization just now. And otherwise, you just want to recursively go in and go to the next node. So this will be, I'll state a result and I'll set it to be equals to the DFS of start plus 1, which is you're going to the next one and plus 1. So plus 1 here means that we skip this character. So as what we have here. So if we skip this A, means that we're treating A as an extra character. So it's also the same right here, right? We're skipping A, so there's an extra character, so we need to plus 1. We need to plus 1, and then we're skipping P again, plus another 1, because we're skipping those and treating them as extra characters. All right, then once we get to some point, we can set current equals to root, because we want to check if that part is actually inside our trie. So for n in range start to n. So we just want to see like, hey, do we have this from like this point up to that point? So we said if Sn not in it, right? So because we just start from start and then going to n, and then we just keep checking, hey, how long is this actually in there, right? And this recursion call is actually setting different starting point over and over again. So if this thing is not in the current.children, means that hey, you go on some point and then it didn't have that, then you might just want to break it. Otherwise, you just want to keep diving down the trie. So you just want to keep move on to the next part of the try. So this is like the question we have before, like the 1, 10, and 100, like the lexical order. So you just keep moving your pointer down the tree, so going down to the children, right? And at the end, if you find that you hit the end or something, so if current dot is word, I think this is when you say something is true, like this part of that is a word, then you can set the result equals to the minimum of your result and DFS calling to the next one. And how this helper method just need to return the result because that's what we're trying to get you to do. And your whole method right here, just want to return the DFS of the start, which is 0, I think. Oh, I just passed 5. All right, I think, yeah, I explained something wrong just now. I don't know why I'm missing this part. Actually, when we do this, you always want to do a current equals current dot children because you want to keep building it next. But when it doesn't have the current dot children in right there, then you want to set the children to be the node. It equals a new node. So you want to set current dot children C equals to a new try node. So I think I'm missing this part just now, and I'm completely blank. So yeah. So if we run this, it's accepted. But one thing when we submit is that you'll get a TLE because of how many times the DFS is actually calling. So it's actually taking a while. So yeah, it's TLE because like this DFS is going crazy. And this is something I learned from the editorial today, and I look it up. And I was like, oh, what is this thing? So it's actually called cache. So it's a function, something that helps you to memorize. It's like DP, but they handle this DP for you. So if we submit again, then yeah, you can see how fast like the runtime improve, and from the TLE, because this cache actually help you to keep all the things that have been computed, and then to just memorize those. So it's called memorization as like a DP. All right, so I hope you enjoyed the video today. I am sorry about like the build try errors just now, but yeah, I'll see you tomorrow.